So in this lesson, we're going to talk about a theorem that in a lot of ways defines the rest of our conversation about polynomials, and that's the rational roots theorem. So I have it written here, and we're going to read through it. If the polynomial p of x equals a sub n x to the n plus a sub n minus 1x to the power n minus 1 plus so on and so forth plus a sub 0, has any rational roots, they are of the form plus or minus p over q, where p is a factor of a sub 0 and q is a factor of a sub n. So as we've discussed before, when we write polynomials, we are going to be writing them in order by decreasing power. So a sub n is the leading coefficient, meaning that it is the coefficient associated with the highest degree term. And then a sub 0 is the constant term. So what you'll encounter is that a lot of the time when you are looking at problems surrounding polynomials, the first step in a problem is going to be, hey, here's a polynomial, write all of the possible rational roots that it has. So you're listing all of the possible ones, and you're not promising that any of them are actually roots. You're just saying if there are any at all, they have to be in this list. So let's try an example like that. So find or list, in fact, let's say list. That's a better word to use here. List all of the possible rational roots of the polynomial 3x to the fourth minus 5x cubed plus 7x squared minus 4. Okay, so notice that we're not actually going to find any of the roots here. We're just going to list all of the possible rational ones. All right, so here goes. P. This is a good way to start this. P, going back to our rational roots theorem, P is a factor of a sub 0. So P is a factor of the constant term. Well, the constant term here is -4, but since we're going to do plus or minus anyway, I'll just look at 4 and then we'll add in the negative later. So what are the factors of 4? There's 1, there's 2, and there's 4. So I'm going to write that here. These are the factors of the number 4, and factors are the numbers that go into it, okay? Now for Q. So looking at the rational roots theorem, Q is a factor of the leading coefficient. Our leading coefficient here is 3, and that's always kind of handy because prime numbers like 3 don't have very many factors. All right, so now let's look at plus or minus P over Q. So what I like to do, and I think that this is just the most meticulous way to do it, is just take every one of the possible values of P and divide it by every possible value of Q. So we have plus or minus 1 over 1, plus or minus 1/3. We have plus or minus 2 over 1 or 2, plus or minus 2 over 3 or 2/3, plus or minus 4 over 1, and plus or minus 4/3. So I want you to notice that there are 6 total. Now, if we actually wanted to test if any of these is a rational root, well, we just finished talking about synthetic division in the last lesson, so we can actually go ahead and use that. So I'm going to take this opportunity to use what we learned in the last lesson. So I'm going to pick one of these, or actually a couple of these at random. We'll say -1 a root, okay, and then after we figure that out, we'll also ask, is 2/3 a root? Okay, So I like to do one example that's a fraction so that you can see that synthetic division is actually pretty quick when it comes to fractions, and it's actually quite manageable. All right, so remember, checking to see whether -1 is a root is the same as asking, is x plus 1 a factor? So I'm not going to write this every time, but what we're saying here is, if I divide 3x to the fourth minus 5x cubed plus 7x squared minus 4 by x plus 1, do I end up with remainder 0? So that's the perfect opportunity to use synthetic division. So remember how we talked about this. So I like to do it with the root written here and then multiply add. That's my preferred approach. So now we're going to write the synthetic form of our polynomial, 3x to the fourth minus 5x cubed plus 7x squared. And now notice there's a skip. It goes from 7x squared straight down to -4. So we're going to put a 0 placeholder where the x term would have been. And then -4 is the constant. All right, here goes. So we know that 3 is going to be the leading coefficient of the quotient. So the 3 comes on down. And then multiply add. So let's see how it goes. All right, 3 times -1 is -3. Oops, I didn't want to do that in red. -3, now add. So we have -8. -8 times -1 is +8. And now we add. And one thing that you're going to be able to start to tell pretty quickly is, even before you've done the whole division, you'll be able to look at it and say, oh, I don't think this is looking good. But because this is really our first example with it, we'll keep going. The reason I said what I just said about, oh, I don't think it looks good, is that you can see that there isn't enough still left over here to where it's all going to cancel out to 0 in the end. You're going to start to be able to anticipate it. But here goes. 15 times -1 is -15. 0 plus -15 is -15. -15 times -1 is +15. And sure enough, the remainder is not 0. So I'm going to say here, this is our remainder. Since the remainder is not 0, -1 is not a root. Okay? Now, we could at this moment say, oh, but look, like there's the quotient, there's the remainder. But since all we were here to do was to test whether it was a root or not, the fact that it's not means our job is done. Okay, let's try 2/3. Maybe we'll have better luck. So here goes, same thing. So we're going to put 2/3 here. And then the synthetic form of our polynomial. Do not forget our placeholder 0. That is in some sense the most important piece. Same as before, the 3 pops down. And same as before, we're going to do multiply add. So one of the things that I hope you're pretty comfortable with at this point is when we multiply 3 by 2/3, the 3's reduce off, and you just have 2. Okay? -5 plus 2 is -3. -3 times 2/3 is -2. 7 plus -2 is 5. And now you can see, and again, I kind of hope that you're starting to get there, that this isn't going to work well. Because look, I have 5 times 2/3, that's 10/3. Well, now I have to add those, and I get 10/3. And now I have to multiply 10/3 by 2/3, and you know when we multiply fractions, we multiply across the top and multiply across the bottom. So we get 20/9. And if you want to see this through to the end, you can. You can say there's 9/9 in every whole, so -4 is -36/9. Negative 36 over 9 plus 20 over 9 is negative 16 over 9. But in a huge way, in a major way, I don't need that. All I can see is that the remainder is not equal to 0. And as soon as I see that, I know that 2/3 is not a root. So I'm not going to go through the whole process of determining whether there's a root or not, for the simple reason that it's not guaranteed that any of these are roots. Which brings me to the last thing that I'm going to tell you in this lesson. If you make a polynomial up off the top of your head, you just think of one. Long, short, doesn't matter. It's very, very likely that it doesn't have any rational roots at all. And when a polynomial doesn't have any rational roots, it is very, very hard to factor it and to find any of its roots at all. And that's part of the reason that polynomials make a really, really great backbone for things like encryption. And polynomials are just number arrays, right? We've seen that with synthetic division. So you'll notice that when we're talking about encryption and security and passwords and things like this, you'll hear about things like 128-bit encryption. Well, what that's talking about is very, very large numbers that are sort of like very, very long polynomials that have very, very few factors, and the factors are hard to find. And in a large way, that very simple fact is an incredibly secure way to protect us in situations where encryption is necessary. If you're curious about that and you want to learn a little bit more about it, there's lots of cool things to read and lots of cool things to learn. Feel free to ask me about it. All right, that's all I got for you. I'll see you in the next lesson.